The 20th century inherited from the 19th a great faith in progress, based on the firm belief that today is always better than yesterday and worse than tomorrow. Around 100 years ago, Marconi successfully develops transatlantic radio transmission. Plastic begins to invade our daily life. Concrete starts being used in construction. The North Pole is reached on foot. The Paris Underground is opened. Ramon y Cajal receives the Nobel Prize for his discoveries in histology. Medical science discovers the existence of blood groups and the causative agents of sleeping sickness, syphilis, and tuberculosis. To sum up, an eclosion of breakthroughs that brought into fashion the phrase, "Today science moves terribly fast." In the field of science, Max Planck, with the formulation on the 19th of October 1900 of quantum theory, opened the door to a new era in physics, with such important figures as Einstein, Rutherford, Bohr or Heisenberg, at a time in which the discovery of X-rays by Roentgen in November 1895 and of radioactivity by Henri Becquerel in 1896 had created great commotion in the scientific community. This last discovery, made by Becquerel, regarding how uranium salts are able to darken isolated photographic emulsions, nevertheless passed mostly unnoticed, and it was not until later studies were carried out by Marie Curie on the radiation emitted by uranium that we were able to conclude that it was necessarily a property of the atom, considered until then to be the smallest indivisible unit of matter, and not the result of molecular or atomic interactions. Thus, the term radioactivity was born, coined by Curie herself. In 1898, she and her husband, Pierre Curie, discovered an element much more active than uranium, which they called polonium, in homage to Marie Curie's native country. That same year, they discovered another, even more active element, which they called radium, although over a decade of hard work treating tons of pitchblende would have to pass until they were able to obtain radium in its pure state. Radon, isolated for the first time by Dawn in 1908, is a gaseous element derived from the radioactive decay of radium, which in turn is a product of the radioactive decay of uranium present in the Earth's crust. We can therefore conclude that our planet is radioactive since its creation around 4.5 billion years ago, although we have not been aware of this until little more than 100 years ago. Studying radioactivity, both Pierre Curie and Rutherford discovered that radioactive substances emit different types of radiation. This discovery enabled us to distinguish between alpha, beta and gamma emissions, and the atom would no longer be considered to be an indivisible unit, having been proved that some elements present in nature, especially those with a high atomic mass, spontaneously transmute into other, lighter elements, freeing energy in the form of particles and electromagnetic radiation originating from their nuclei. In 1934, the year of Marie Curie's death, her daughter Irene Curie discovered, together with her husband Frédéric Joliot, artificial radioactivity, the possibility of creating radioactive elements in the laboratory. This discovery has undoubtedly had a great impact on our society, as the use of this kind of elements, both in medicine and in industry, has made a substantial contribution to their advancement. Today, the use of artificial radioactive elements in the diagnosis and treatment of diseases and in industrial processes of great social interest is commonplace. A good example are the smoke detectors used in fire prevention. It is difficult, however, to change the common thought among the public of radioactivity as unequivocally linked to productive activity, and in many cases, to the most negative side of human behavior, due to the horrible consequences of the atomic bombings of Hiroshima and Nagasaki. The truth is that often when dealing with this issue, we forget that radioactive emissions present specific characteristics aside from the fact that the element in question is of natural or artificial origin. There are three main types of radiation emitted by radioactive elements: alpha, beta and gamma. Alpha rays, charged particles consisting of 2 neutrons and 2 protons, are emitted by the nuclei of elements with high atomic numbers, such as uranium, thorium, radium or radon. Due to their mass and speed, when alpha particles pass through matter, they are quickly slowed down, thus producing a high level of ionization by freeing electrons from the atoms with which they interact. For this reason, protection against this type of radiation that can be easily achieved even with a thin piece of paper or a few centimeters of air is more complicated when the element emitting the radiation is inside our body. Beta radiation, due to electrons, presents, as a consequence of their smaller mass, a higher penetrative power in matter than alpha radiation. The ionization it produces is lower, and as a consequence, a few meters of air or sheets of thin aluminium are required to stop it, and it is capable in the human body of penetrating the skin to a depth of several millimeters. Finally, we have gamma radiation. It is an electromagnetic and very energetic form of radiation and presents a very short wavelength, with a much higher penetrative power than alpha and beta radiation. It is capable of completely passing through the human body, and meters of concrete are required to stop it. According to Mendelev's table, radon belongs to a group of noble gases, so called because of the absence of chemical radioactivity in this type of gas. Radon also presents this attribute, but is at the same time extremely mobile, capable of passing through plastic, wood or concrete walls in more or less time, depending on the material. Radon is present, although in a very small proportion, in the air that we breathe. It is colourless, odourless and tasteless, and has a moderate solubility level in water. It is formed by the decay of radium-226, which in turn derives from the decay of uranium present in the Earth's crust. It has a semi-disintegration period of 3.8 days, which means that by that time its number of atoms is halved, as it disintegrates, emitting alpha radiation, and producing new elements, which in turn also decay, emitting alpha, beta and gamma radiations until, at the end of this decay chain, it reaches a stable element, lead, with a mass number of 206. Through breathing, radon and its daughters penetrate in the respiratory system, and while the first stays in the body for a very short time, the seconds settle on the internal surfaces of the airways, completing their decay process and harming the cells with the radiation they emit. This is the key factor in radon's harmful effects on our health. Due to its period of half-life, that is to say, its radioactive character, for there to be a continuous presence of radon in a given area, it is necessary for this gas to be continuously forming. This is why if we want to have more information about the origin of radon in our homes, we must first determine the location of the uranium from which it derives. Uranium is a very chemically active element, capable of association with many others and of moving with them. Uranium is found in almost every rock and soil on our planet, generally in small proportions of a few grams per ton, depending on the rock and soil type, except in those areas in which its abundance is commercially exploited. So, the first clue towards locating uranium is provided by the analysis of the geological chart, which gives us information on the types of rocks present in the area which we are studying, and secondly, on the levels of gamma radiation emitted by the isotopes of the series. These parameters on their own are, however, insufficient for the evaluation of the amount of radon which penetrates into our homes. The decay of uranium atoms produces radium atoms, but, as both are solid, neither can move if it is not together with the rock or soil they are part of or dragged by underground water currents. Radon atoms, however, being gaseous, can move freely while they decay, giving way to their daughters. This movement of radon atoms will be slower or faster depending on the particular conditions of the rocks or soil in which they are found. Very fractured rocks and porous soils, for example, will present little resistance to the movement of radon, enabling it to reach the surface easily and, in consequence, the outside air. Once outside, the enormous volume of air in our atmosphere is capable of diluting the radon exhaled from the Earth, making the atmospheric concentration of this gas, on the most part, very low. Soil permeability is the parameter which determines the level of difficulty it presents to the passing of fluids and constitutes the main factor when evaluating radon emanation. As clays, for example, contain a significant concentration of uranium, they are a potential source of radon. However, their high impermeability level means that the amount of radon that reaches the surface is very small. In contrast, in very permeable rocks such as limestone that have an uranium content around 10 times lower than clays, radon moves more easily and can reach the Earth's surface in a higher proportion. The same happens with granite. Although it has an important uranium content, it presents a structure that minimizes the amount of radon escaping when it is compact. This is what happens, for example, with the worktops made from this material found in our kitchens. The amount of radon which escapes increases significantly when the granite is fractured or ground. In consequence, the content of uranium, and therefore of radium, the porosity and the permeability of the soil are important factors which determine the presence of radon in homes. Taking everything into consideration, the main source of radon inside our homes is the soil on which these are constructed. The second source of this gas is the construction materials used to build houses, and as their uranium content basically depends on the area from which they come from, areas might exist in one same country where the contribution from materials is as important a source of radon as that of the type of soil. Doubtless, this fact can gain more importance if we consider the new sources of construction materials, countries with a high content of natural radioactive elements. Finally, as radon dissolves in water and is also easily eliminated by means of agitation or heating, water can become a significant source of radon when it emanates from deep wells and hasn't undergone previous purification processes. Whether the main source of radon originates from the soil under our homes or the construction materials used to build them, the penetration of this gas takes place through processes of molecular diffusion and convective transportation due to pressure gradients. We will try to explain the basis of both processes. The disintegration of the radium present in soil or construction materials is logically the starting point, as it is responsible for a fraction of radon atoms abandoning the solid environment where they are generated, reaching the pores of the earth or of the material, and moving through them to the surface. Molecular diffusion basically entails the movement of radon atoms from those areas where their concentration is higher to others where it is lower. In our case, radon gas concentration is higher in soil and practically inexistent in the outside air. The basis of convection, in contrast, is the difference in pressure between the gas in the soil and the inside or outside of houses. As the pressure inside houses is slightly lower, due to the wind or the use of heating or ventilation systems, radon is dragged by pressure differences through the pores, fissures and cracks in the structures that separate houses from both the soil underneath and the outside. Once we have outlined the main parameters which determine the presence of radon in homes, the following facts are easily understood. In periods of strong rain, the pores in the earth saturate and the amount of radon which reaches the surface decreases. A lowering of atmospheric pressure, caused by the presence of wind for example, will provoke a supplementary emission of radon from the earth as a consequence of convection, due to pressure differences between the soil and the air. Also, the difference in temperature between inside and outside the houses will maximize radon concentration in the early hours of the morning. All these factors, together with the different ventilation conditions of houses during the winter and summer months, explain the elevated concentrations recorded during winter, which, on average, can exceed those recorded in the summer by a factor of 2. According to what we have seen, the problematic of radon in homes will, in general, only exist when they are built near a soil which is an important source of radon. That is why this problem does not usually appear in blocks of flats, characteristic of cities. The existence of radioactive elements, and specifically of radon's precursors, is inherent to the presence of man on the Earth. This has determined that long before radioactivity and its harmful effects were discovered, some scientists had already, unknowingly, detected their presence. In 1556, one of these scientists, Agricola, in the first study carried out in relation with prospection in mining and metallurgy, pointed out the high incidence of lethal lung diseases among pitchblende miners in Drogi Mestal, Czech Republic, where this mineral, one of the main sources of uranium, was extracted. We can all imagine a mine with enormous amounts of uranium, poorly ventilated shafts, and very high radon levels. Radioactivity and, in consequence, radon were present, but Agricola could not know that then. It was not until the mid-20th century that the need for uranium as fuel for nuclear power stations determined the mining boom that the number of workers exposed to radon in mines multiplied. The first scientifically based knowledge of the radon problematic stems from the development of the nuclear industry, and this is also the origin of its interest from a social perspective. Let's go back in time a few years. It's 1985 in Pennsylvania, United States. Stanley Watrous headed to the nuclear power plant where he worked. As was compulsory, he passed through the radioactivity detectors present both at the entrance and the exit. The alarm went off, and he asked himself, "Am I contaminated?" This seemed impossible. He was going to work from his house. but it was precisely there where he had been contaminated. The radon in his house, in a level hundreds of times greater than that in the uranium mines, had contaminated with its daughters his clothes, and that is why the alarm detected its presence and went off. This was when radon measurement campaigns in homes were first implemented in many countries to determine its concentration and the areas with a high potential risk. We must not forget, however, that the precursors of these campaigns were the northern countries, which, at the beginning of the 1970s, began studying radon concentrations in homes. During those years, coinciding with the petrol crisis and due to the low temperatures at those latitudes, the construction industry underwent an important transformation, due to the fact that, for energy-saving reasons, houses were built more hermetically, thus increasing the concentration of radon inside to sometimes very high levels. More than 20 years later, in countries such as ours, with less extreme temperatures but the same energy problem and high price of urban land, a similar phenomenon has taken place. As a means of comparison, while the air inside an old house is renewed around 3 times per hour, a modern home requires 2 hours for that renovation to be carried out. This favours the presence and build-up of radon inside. If we also take into account the increase in the use of construction materials, especially those imported, derived from industrial waste products such as ashes from thermal energy plants or the iron industry, or products originated in the fertilizing industry with a high radium level, we can understand why it is becoming more important to establish a radiologic control of these materials in order to prevent and reduce the presence of radon gas inside our homes. This necessity is identified in the draft of the Euratom Basic Safety Standards Directive, in which the International Atomic Energy Agency participates. Various methods are used to measure radon concentration. Instantaneous methods enable us to determine its concentration at a given moment. They use cells placed in a vacuum with which air samples are taken in the selected location. Next, as the internal surface of these cells is covered with a special substance called zinc sulfide, the interaction of the alpha radiation emitted by radon and its daughters with this material generates electric pulses, which are detected by an electronic device by means of which radon concentration is calculated. Activated carbon is a material capable of absorbing gases such as radon. If we place a certain amount of activated carbon in an atmosphere containing radon for a certain exposure period, this gas will be retained, enabling us to determine its concentration in the air by measuring the exposed carbon in a gamma spectrometry chain, where the gamma radiation emitted by radon, bismuth-214 and lead-214 is measured. The sensitivity of this method of measurement implies a period of exposure of a minimum of 3 days and a maximum of 7. This is why the concentration measured only represents that period of time, and it is a screening method frequently used to identify houses with high radon levels. When our objective is to determine radon concentration over a sufficiently long period, let's say months, we use traces, inside which a sheet is placed that is sensitive to the alpha radiation emitted by radon and its daughters. When the exposure period concludes, the sheet is subjected to a chemical treatment, and after its development, the traces produced by the alpha particles emitted by radon and its daughters are counted using sophisticated equipment. This is an integrated method, which allows us to determine the average radon concentration in the place of choice. The use of one method or another basically depends on the desired objectives. So, if what we want is to quickly establish if radon is present in an area, or whether the construction materials represent an important source of this gas, we should use the cell or activated carbon methods. If what we want is to establish the average radon concentration, trace detectors are more appropriate. Whatever measurement method is used, its calibration is imperative. To achieve this, intercomparison campaigns between laboratories have been established on a worldwide level, using reference chambers such as the one found in the Institute for Energy Studies at the Polytechnic University of Catalonia, which has as a final objective the control of measurement quality. The result of the measurement of radon concentration, whatever the method used, is a numeric value, usually expressed in becquerels per cubic meter. The becquerel is the unit used in radioactivity equivalent to 1 decay per second. Using the concentrations measured as a starting point and applying the appropriate conversion factors, it is possible to calculate the dose received as a consequence of the presence of radon in the air. In the field of radioactivity, the dose measured in millisieverts is the magnitude which takes into account not only the physical characteristics of the radiation received, but also the biological harm produced. During the course of 1 year, not only radon gas contributes to the dose we receive as a consequence of living on our planet. We are also subjected to external radiation from soils and construction materials, to cosmic radiation and internal radiation, due mainly to the radioactive potassium that is part of our bones. These are all natural sources of radiation. In addition to these natural sources of radiation, we are subjected to others of artificial origin. Of these, the most important is due to medical exams, such as X-rays, scintigraphies, and others of a radiological nature. Another important artificial source is found in nuclear power stations and rain, which carries with it radioactive elements present in the high atmosphere that fall to Earth and end up entering our food chain. On average, we can estimate the contribution of each of these sources of radiation to the annual dose as follows: 1.1 millisieverts by the inhalation of radon and its daughters, 0.1 millisieverts due to thoron and its daughters, 0.4 millisieverts by cosmic radiation, 0.4 millisieverts by internal radiation due to the potassium present in our organism and the ingestion of other natural isotopes, 0.5 millisieverts by external radiation emanating from soils and construction materials, 0.4 millisieverts due to medical exposure, 0.01 millisieverts due to the impact of nuclear power plants and radioactive rain. In total, the average annual dose can be estimated to be 2.9 millisieverts, of which 2.5 are due to natural sources from which there is no escape. Of course, these dose values respond to an average situation. If the radon levels in the house we live in are high, we undergo a high number of X-ray scans, we live at high altitudes or in places with high concentrations of radioactive elements in the soil or in construction materials, the dose received will be considerably higher. The same would happen to us if we were to work in environments with high levels of natural radiation, like mines, plains, caves or spas. With these facts, one logical question arises. What is the dose below which we can consider ourselves to be safe from a radiological perspective? The scientific community hasn't provided up until now an answer that is completely satisfactory, but it does provide us with experimental data. At the beginning of the 1930s, the first articles were published confirming what had been until then a suspicion, that uranium miners suffered lung disease in a higher proportion than the general population. There was a relationship between the disease and the high radioactive content of the air and the water in the mines. With the development of this type of mining, after the Second World War, the first epidemiological studies were carried out, monitoring mining populations for many years in different parts of the world. One of the most important took place in Colorado, United States, during the 1960s, 70s and 80s, and it confirmed the close correlation between the presence of radon in mines and lung cancer among the miners. An increase in incidence was found by a factor of 10 in relation to the general population, reaching 30 when tobacco was added to radon exposition. In all cases, the doses received by the miners were in the region of hundreds of millisieverts per year, far higher than the 20 millisieverts per year, which is the maximum recommended dose in this activity as recommended by international bodies. The basic issue is to determine whether these risk factors can be applied to the general population living in houses where, in general, radon levels are lower and the environmental conditions are very different. Recently published scientific studies, which provide data from different epidemiological tests, seem to confirm the hypothesis. The World Health Organization reaffirms this after 3 years of intense investigation by the International Radon Project, with the participation of scientists from more than 30 countries. In an official document, the WHO recommends radon levels in homes lower than those proposed by the European Union. The truth is that even though the main cause of lung cancer is tobacco, the presence of radon gas in homes is responsible for between 3 and 4% of the total number of cases. The International Commission for Radiological Protection, in its latest meeting held in November 2009, has alerted of the importance of radon gas in the dose received by the population, proposing a reduction of this gas in homes in comparison with its publications 39 and 65, which had established the guideline until then. Without a doubt, these two facts bring into question the proposal made by the European Commission in its recommendation of the 21st of February 1990 on protection of the public from exposure to radon in interiors. In this recommendation, a reference level of 400 becquerels per cubic metre was set to consider restorative actions in existing homes, and a design level for future homes of 200 becquerels per cubic metre, understanding both values as average annual concentrations. From what we have seen, it seems that this recommendation is going to suffer important changes in the near future, towards the reduction of radon levels both in existing and in future houses. In Spain in the early 1990s, as in all other industrialised countries, radon measurement campaigns were carried out funded by the Nuclear Safety Council, in houses in the Valencia region, the Canary Islands and the cities of Madrid and Barcelona by the universities of Valencia, La Laguna, the Autonomous University of Barcelona and the CIEMAT. Also, a nationwide measurement campaign was carried out by the University of Cantabria, funded by the European Union, the National Research and Development Programme and the Nuclear Safety Council. On the basis of these measurements, an average value was found, expressed as a geometric radon concentration average of 41 becquerels per cubic metre, similar to that of other countries in our area of influence. Since then, and with the exclusive funding of the European Union and the Nuclear Safety Council, the University of Cantabria has carried out specific measurement campaigns in areas surrounding nuclear power stations, granitic areas such as La Vera, and uraniferous regions like La Haba and Cardeña, as well as the specific areas of Los Arribes del Duero, Sierra de Guadarrama and Galicia. Additionally, with funding from the Galician Regional Government and the Nuclear Safety Council, the Preventive Medicine and Public Health area of the University of Santiago de Compostela has carried out 2 radon measurement campaigns in Galicia. Today, funded by the Nuclear Safety Council, an expansion of Spain's radon map is being developed by the University of Cantabria, Santiago de Compostela and the Autonomous University of Barcelona. This expansion will provide a measure of radon concentration in at least one home in a 10 by 10 kilometre grid. In total, 8,000 new radon gas measurements will be made available, adding to the approximately 10,000 that already exist. However, as we have already mentioned, while we wait for the results of these studies, predicted for the beginning of 2012, it seems necessary, as has been done in other countries, to reduce radon levels in houses where these are higher than the recommended values using restorative techniques. We should also design a technical building code with specific criteria and construction rules for these areas to not further enhance the radon gas problematic. To sum up, prevention rather than restoration, which is always more expensive and complicated. To synthesize everything we have said, we must distinguish between what has been scientifically proven about radon and those other aspects which require definitive confirmation. Regarding radon, the following aspects have been scientifically confirmed and are, as a result, accepted: its origin, its physical and chemical properties, and its nature as a cancer agent. The dose, due to its presence in the air we breathe inside buildings, represents around 50% of the total dose received by the population as a consequence of exposure to radiation of a natural origin. Its presence in elevated concentrations in the air in uranium mines makes it responsible for a significant increase in the worker's risk of developing lung cancer. In contrast, further research is required in the field of radon in order to identify and locate in the respiratory system the target cells on which radon and its short-lived progeny act more specifically. Determine the radiation dose received by cells with higher precision. We must confirm whether, as indicated by the WHO, radon is responsible for between 3 and 4% of all cases of lung cancer. We must precisely identify potential risk areas due to exposure to radon in the country and take further action in homes if it is required. While we await the results of these investigations, the best way to minimize radon's effects in homes is prevention. Prevention mainly comprises the correct definition and evaluation of its sources and an adequate building design which will deem radon level reduction techniques unnecessary once they are built. As all sectors of society are involved in these preventive tasks, it is clear that radon is and will continue to be an issue of great interest for all of us.